There's a photo that should exist by now, but it does not. It's not because the technology is missing, it's not because the distance is too far. It's a simple photo of our own solar system taken from above, looking straight down at it the way you'd look down at a plate on a table. And here's the part that sounds made up, but is completely true. It would be easier, cheaper, and faster to send a spacecraft all the way to Pluto than to send one straight up above the sun. Going up costs more fuel than flying to the edge of our solar system. Read that again. Going up is harder than going almost anywhere else humans have ever sent a machine. So why has nobody done it? Why, after 70 years of space travel, after landing robots on Mars, after flying past every planet, do we still not have a single clear photo of our solar system from above or below? The answer involves a speed you're moving right now without feeling a thing. It involves a wild trick where the only way to escape is to dive straight toward danger first. And it involves one single mission that, just very recently, sent back the first real photos ever taken of a part of the sun no human eye had ever properly seen before. By the end of this video, you will understand why the direction up in space might be the strangest, most stubborn wall humans have ever run into. And you will understand the clever plan that scientists think could finally break through it. Before we get into that, if you like learning about the weird hidden rules of space, the kind of stuff that sounds fake but isn't, hit subscribe now. This channel is going to keep digging up these strange corners of science that never made it into your school textbook, and you don't want to miss the next one. Let's start with the reason going up is so hard in the first place. The flat frisbee we're all riding on. Here's something almost nobody thinks about. Our solar system is not shaped like a ball. It is shaped like a flat frisbee. The sun sits in the middle. Every planet, every moon, every asteroid, and almost every comet all circle around it on the same flat level, like plates stacked on a table. Except they're not stacked. They're spread out sideways in one big flat ring. Nothing floats way above the sun. Nothing sits way below it. Everything stays roughly on the same flat sheet. This didn't happen by accident. A long time ago, before there were any planets at all, there was just a huge spinning cloud of gas and dust. As that cloud pulled itself together with gravity, it kept spinning faster, the same way a spinning skater speeds up when they pull their arms in, and spinning things naturally squash themselves flat. Think about pizza dough. When you spin it in the air, it doesn't stay a ball, it flattens out into a wide, thin circle. That is exactly what happened to the cloud that made our solar system. It spun itself into a big, flat disk, and the sun and all the planets formed out of that disk. That's why they all still circle on roughly the same flat level today. Now here's where it gets interesting for us. Earth is part of that flat, spinning disk, and because Earth is part of it, Earth is not just sitting still. Earth is racing sideways around the sun at about 18 miles every single second. Not every hour, every second. You cannot feel it because everything around you, the ground, the air, the ocean, the whole planet, is moving at that same speed together, like being on a smooth train with the shades down. But that speed is real, and it is enormous. Here's the part that changes everything. Every rocket that has ever launched from Earth was already moving at that same sideways speed before it even left the ground. It didn't need to build that speed up. It was born with it, just from sitting on a launch pad on a moving planet. So when a rocket lifts off, it's not starting from zero. It's starting already sprinting sideways, and everything it does afterward just tweaks that sideways motion a little bit. Go faster sideways and you drift out toward Mars or Jupiter. Go slower sideways and you drift in toward Venus. Either way, you're still moving along the same flat disk the whole solar system shares. But what if you wanted to go a totally different way? Not out toward the edge, not in toward the sun, but straight up, out of the flat disk entirely, into the empty space above or below it? To do that, a spacecraft cannot just add a little push. It has to cancel out almost all of that huge sideways speed it was born with, the same 18 miles per second every rocket already carries, and replace it with speed in a brand new direction, straight up. That is an enormous, brutal amount of work. It is like trying to make a car driving down the highway suddenly drive straight up a wall instead. The car already has all this forward momentum built in, and turning that into upward momentum takes way more force than just speeding up or slowing down ever would. This single fact is the reason nearly every spacecraft in history has stayed inside that flat disk. Going out to the edges is expensive but doable. Going up is a whole different level of hard, and once you understand just how hard, the numbers get almost funny. Why? Up is the hardest direction in space. Let's put this in terms that actually make sense. Scientists measure how expensive a space trip is by how much a spacecraft's engines have to change its speed. Think of it like a budget of energy the spacecraft is allowed to spend. Every turn, every speed up, every slowdown eats into that budget. Once the budget runs out, the spacecraft can't do anything else. It just drifts wherever its last move sent it. Getting off Earth and into a basic orbit around our planet already eats up a huge piece of that budget. all just fighting gravity and air on the way up. From there, going to the moon costs a bit more. Going to Mars costs more still, but honestly, not that much more, especially if you launch at the right time when the planets line up nicely. Going all the way out to Jupiter costs more again, but it's still something rockets have managed again and again for decades. Now here's the twist. Going all the way out to Pluto, one of the most distant objects we've ever sent a spacecraft to, costs less than trying to fly straight up out of the flat disk to a height no greater than Earth's own distance from the Sun. Read that one more time too, because it sounds backwards. Flying to the far edge of the solar system is actually cheaper in fuel terms than flying straight up a short distance above the Sun. Why would that be true? It comes down to which direction the Sun's gravity is already helping you. If you want to go outward, toward Jupiter or Pluto, you can just nudge your speed up a little bit in the direction you're already moving. Your orbit slowly stretches out wider and wider, like slowly loosening a rubber band, and the Sun's own gravity does almost all the actual work, pulling and guiding you along the way. It's a gentle nudge, not a shove, but going straight up is nothing like that. None of your existing sideways speed helps you at all. None of the Sun's gravity helps either, because the Sun's gravity pulls everything straight toward its center, not up and out of the flat disk. Every single bit of upward push has to be paid for completely, in full, with fuel burned in space, and there is no shortcut, no gentle assist from gravity to lean on. So the Sun's north and south, the very top and bottom of our whole solar system, sit in a strange kind of trap. They are not far away in terms of raw distance. The top of the Sun is roughly the same distance from Earth as the side of the Sun we already study all the time. But almost nothing has ever visited it, because reaching it means fighting against the exact motion that built the entire solar system in the first place. There is one clever workaround though, and it's the reason we've ever gotten close at all. Scientists discovered that if you fly a spacecraft close past a massive planet like Jupiter, that planet's gravity can grab your spacecraft and fling it off in a totally new direction, for free, without burning any extra fuel. It's like grabbing a moving merry-go-round for a second and getting flung off sideways with extra speed. Jupiter is so massive that a close flyby can genuinely bend a spacecraft's path up and out of the flat disk. Smaller planets like Venus can do a gentler version of the same trick. One flyby past Venus doesn't bend the path very much, but if a spacecraft loops back and flies past Venus again and again over several years, each pass bends the path a little more, slowly climbing the spacecraft up and out of the flat disk bit by bit. It's slow, it might take years, but it costs almost no extra fuel, just a lot of patience. These planetary flybys are basically the only reason humans have ever managed to send anything, even partway toward the Sun's poles at all. Which brings us to the real question: what exactly is hiding up there that's worth all this trouble? The secret top and bottom of the Sun. Almost everything we know about the Sun comes from looking at its middle, the wide belt around its equator. That's where the sunspots are. That's where the giant eruptions we see in photos come from. That's what every solar telescope on Earth has been staring at for hundreds of years. But the top and bottom of the Sun, its poles, behave completely differently, and scientists have only recently started to get a real look at them. Here's the first big surprise. The fastest wind in the entire solar system blows straight out of the Sun's poles, not the middle, the top and bottom. The Sun is constantly blasting out a stream of tiny charged particles in every direction, called the solar wind. Near the Sun's equator, this wind is kind of slow and choppy, drifting out at somewhere around 300 to 500 miles a second. But from the poles, the wind screams outward at 700 to 800 miles a second, almost twice as fast, in long, steady streams instead of choppy gusts. For decades, scientists could only guess this was happening based on math and models. Nobody had actually flown a spacecraft up there to check until fairly recently. Here's the second big surprise, and it's an even stranger one. Every 11 years or so, the Sun's entire magnetic field flips completely upside down. What was its north pole becomes its south pole, and the other way around. This isn't a small wobble. It's a full flip of the Sun's entire magnetic identity, and it happens like clockwork, over and over, forever. And where does this flip actually begin? At the poles. The magnetic flip starts up at the top and bottom of the Sun and slowly spreads from there. So the poles aren't just some quiet, boring edge of the Sun that nothing interesting happens at. They are basically the control room. Everything dramatic that happens on the Sun's visible surface, the flares, the sunspots, the outbursts that can mess with satellites and power grids here on Earth, all of it traces back to processes that start at the poles and work their way down. There's also something bigger going on that stretches out into the space around the whole solar system. The Sun's magnetic field doesn't just sit near the Sun, it stretches outward for billions of miles. And because the Sun rotates, that stretched out field twists into a giant wavy shape, kind of like the swirling, rippling hem of a spinning ballerina's skirt. This giant wavy sheet sweeps past every planet in the solar system, including Earth, again and again as the Sun spins. Near the poles, this wavy sheet flattens out and calms down. Near the equator, it ripples and flaps around wildly, but almost everything we know about this giant structure has been figured out sideways, by spacecraft sitting inside the flat disk looking out at it edge on, never from directly above or below where you could actually see its true shape. So think about what we're really missing here. The fastest wind in the solar system, the place where the sun's magnetic flips begin, and the true shape of a magnetic structure bigger than the entire solar system, all of it lives at the poles, and almost none of it has ever been seen up close. Which raises an obvious question. Has anyone even tried to get up there? Yes. Exactly. 2 spacecraft in all of human history have ever made a real attempt, and their stories are both incredible and a little bit heartbreaking, because both of them only managed to get part of the job done. The 2 machines that tried. The first spacecraft to ever seriously climb out of the flat disk launched decades ago, and its plan was bold almost to the point of being reckless. Instead of heading toward the sun, it launched the opposite way, out toward Jupiter on a long multi-year journey. When it finally reached Jupiter, it used that planet's massive gravity to slingshot itself onto a totally new path, tilted a wild 80 degrees compared to the flat disk almost straight up and down relative to everything else in the solar system. No chemical rocket could ever have bent a path that sharply on its own. It would have needed way more fuel than any spacecraft has ever carried. Jupiter's gravity did it for free. From there, the spacecraft spent years looping high above the sun and then dipping low beneath it, sweeping past the poles that no machine had ever visited before. And the discoveries were huge. It proved, for the first time with real direct measurements, that the fastest solar wind really does come from the poles, exactly like the models had guessed. It also confirmed that giant wavy magnetic skirt really does calm down near the poles just like predicted. It flew through regions of space that had literally never been sampled by any human-made object before. But here's the catch. That spacecraft carried instruments to measure things like wind speed, particles, and magnetic fields. It did not carry a proper camera. So even after nearly 20 years flying above and below the sun, it never once took a real photo of what the poles actually looked like. It proved the poles were strange and important. It just couldn't show us a single picture of them. Decades later, a second spacecraft launched with a very different plan and a very different toolkit. Instead of one dramatic slingshot around Jupiter, this one uses a slow, patient trick, flying past Venus over and over again, letting each flyby bend its path just a little bit more out of the flat disk. It's a slower climb, spread out over many years, but it costs far less fuel. And this time, the spacecraft was packed with cameras and imaging tools built specifically to finally photograph what the first mission could only measure. A heat shield protects it from the brutal sunlight when it swings in close to the sun, with small doors that pop open briefly to let the cameras peek out safely. Just recently, after years of slowly climbing higher and higher, this spacecraft finally tilted enough to catch its first real close, direct photos of one of the sun's poles. Ever. In the entire history of humanity looking up at the sky. And what came back did not look like the sun we're used to. The middle of the sun, the part we've always studied, shows big, organized dark spots and huge looping eruptions. The pole looked completely different. The surface was messier, finer, more chaotic, covered in countless tiny tangled threads of magnetism instead of big organized ones. Thin streams of glowing gas stretched outward from the pole, like blades of grass all leaning the same way. It was, quite literally, a part of our own sun that human eyes had simply never properly seen before that moment. So between these 2 missions, we finally have proof the poles are real, strange, and important, and we finally have our first true photos of what they actually look like. But here's the thing. Neither spacecraft could ever hover in place and just watch. Both were always moving, sweeping past quickly before curving back down into the flat disk again. Nobody has ever sat above the sun's pole and just watched it for a long stretch of time. And nobody has ever taken that one big photo, the flat plate view of our whole solar system from above, looking down at every planet at once. So, if going up is really this hard, is there any real hope of ever getting that photo? It turns out, yes. And the answer involves one of the strangest tricks in all of space travel. The trick that could finally crack it. Here is the idea that might finally break this whole problem wide open, and it sounds completely backwards at first. If you want to escape the flat disk and fly up and away from the sun's grip, the best move is not to fly away from the sun first. It's to dive straight toward it. Here's why that actually works. When a spacecraft fires its engine, the amount of extra energy it gains from that burn depends on how fast it's already moving. Burn your engine while moving slowly, and you get a small boost. Burn the exact same engine for the exact same amount of time while moving extremely fast, you get a much, much bigger boost. It's not magic, it's just how energy and speed are connected. Going twice as fast doesn't just double your energy, it multiplies it by 4. And there's no place in the entire solar system where a spacecraft moves faster than right next to the sun. As you fall in close to the sun, its gravity yanks you faster and faster, whipping you around at incredible speed. If you fire your engine at that exact moment, right at the closest point, that tiny burn gets turned into a giant burst of extra energy, way more than the same burn would ever give you out near Earth. So here's the plan. A spacecraft launches from Earth and lets itself fall inward toward the sun, picking up huge speed the whole way down, almost like a ball rolling down into a canyon. Right at the bottom, the closest point to the sun, it fires its engine for just a few minutes. Because it's moving so incredibly fast at that moment, that short burn delivers a massive kick, way bigger than firing the same engine anywhere else in the solar system ever could. And that kick can be aimed straight up out of the flat disk, sending the spacecraft climbing toward the poles on a path that would have been almost impossible to reach any other way. The savings are honestly hard to believe. A straight-up climb that might normally cost a spacecraft nearly its entire fuel supply could instead be done with a small fraction of that, all because the burn happens at exactly the right moment, deep in the sun's gravity, where speed does most of the work for you. The catch, of course, is survival. Diving that close to the sun means facing brutal heat, and any spacecraft attempting it needs a serious heat shield to survive the trip and still function well enough to fire its engine at exactly the right second. That kind of shielding has already been built and tested successfully on real missions, so the technology isn't science fiction anymore. It's just expensive and hard to pull off perfectly. There's also a second option that doesn't need any fuel at all. Instead of an engine, a spacecraft can use a giant, super-thin, mirror-like sail that catches the gentle push of sunlight itself. A single beam of sunlight barely pushes it all, but spread that push out over a sail thousands of square feet wide and let it add up patiently over months and years, and it becomes enough force to slowly bend a spacecraft's path, tilting it further and further out of the flat disk over time. It's slow. It might take years longer than the dive and burn method, but it never runs out of fuel because as long as the sun is shining, the sail keeps pushing. So picture for a second that one of these missions finally gets built and flies all the way up above the sun's pole, hovering there for years instead of just sweeping past. What would it actually see? Looking down, for the very first time ever, it could photograph the entire flat disk of our solar system laid out below it like a plate on a table. Every planet's orbit visible at once, the asteroid belt showing up as a faint ring, the whole layout of our cosmic neighborhood captured in a single image that has simply never existed until now. Looking outward, away from the sun, the sky itself would look strangely clean and dark, clearer than any view we can get from Earth, because from up there the faint, glowing dust that normally clutters our view from inside the flat disk would be left behind below. That cleaner view could help telescopes spot fainter stars, fainter planets around other stars, and even see the faint leftover glow from the very beginning of the universe more clearly than ever before. And it could finally answer one of the biggest remaining mysteries about our own solar system. The giant bubble of solar wind that surrounds our entire solar system and shields us from the harsher stuff floating around in the rest of the galaxy has never actually been seen from outside. Scientists aren't even sure what shape it really is. Some think it trails behind us like a long comet's tail. Others think it's shaped more like a squashed, curved croissant with no tail at all. Nobody knows for sure, because every single measurement we have ever taken of this bubble has come from directly inside it, sideways, never from above or below where you could actually see its full outline. All of this, the full photo of our solar system, the true shape of the bubble that protects our entire planet, the clean view out into the rest of the universe, is sitting right there waiting for us. It's not blocked by distance. It's not blocked by impossible technology. It's blocked by one single stubborn direction that our entire solar system has been fighting against since the day it formed. Up! The trajectories have already been calculated, the heat shields have already been tested, the sails have already been proven to work in smaller tests. What's missing isn't the science. It's the decision to actually build one of these missions and fly it. So somewhere out there, above the sun's poles, empty space is quietly waiting for the day we finally decide to look. If this kind of space mystery gets your brain buzzing, hit that subscribe button and turn on notifications so you don't miss the next one. And here's a question for you down in the comments. If scientists could only build one of these missions, the dive and burn version or the patient solar sail version, which one would you pick and why? Drop your answer below. I'd love to see what you think. Thanks for watching, and I'll see you in the next one.